You're watching a physics introduction series. This is the first one of the series. Our goal is to help those who are, the optimum people to listen to this are those who are going to high school from middle school. For those who have been in middle school for at least for junior, it's probably too late. Freshman and sophomore, I don't know. For those who are sixth graders and seventh graders, okay, but sixth grader or the elementary school kids are probably too young to deal with this stuff. The purpose is for this crowd who these people who are going to learn mathematics and physics at the high school level to have a overall picture of what they're getting into. The problem with many people think that the math is hard, physics is hard. The problem about this thinking, part of it at least, is that people don't really have the overall picture when they study the so to speak. People study nuts and bolts. They don't know what machine they're going to build in the end. Because nuts and bolts is very easy. I teach you this nuts and bolt, and then I can give you exam questions, and things can be done. I can have a curriculum. I told you you learn this piece and this piece and this piece, but however you're going to use it later, that's not my problem. I think it contributes a lot to the sort of impression that math is hard. But once you don't have math, then you don't have physics anyway. The purpose of this series is to give people an idea of the overall picture. So you ask the question, how are you going to get hold of the idea of the machine if you don't even know the nuts and bolts? That's a very valid question. I don't know the answer, but I think the attempts need to be made. The imperfect attempts need to be made because, for instance, let's just use an example of foreign language education. You can learn a foreign language through these grammars, whatever. But many people, they learn this for a year, 2 years, 3 years, 4 years, and they go to another country and they don't understand the thing. A better way to learn it, I think, is you listen to the other language, the foreign language. And while you're listening to it, you try to get hold of the idea that they're expressing, independent of grammars or whatever. And if you do this for 3, 4, 5, 6 months, you will pretty much get hold of the general idea of what they're saying. Then you can go to those countries and live. And I don't mean live in terms of making money. I mean live in terms of you can find your hotel and find bathroom, restaurants, you can pay bills and stuff like that. And actually, that's how I learn languages, and then I go visit the country, and it all works. Physics is the same situation. That schools cannot teach language this way because for the first 6 months, probably, there's nothing to show for it. For at least the first couple of months, there's no way the student's going to get anything. So you ask the student, what did you get? I mean, we just give them some language, and then there is an issue that you have to listen to it closely. You have to really try to listen to it to get the language. If you just doze off, then you'll never get the language. Doesn't matter how many months you listen to it. So that's the problem the school has to deal with, and all that contribute to this problem that you learn grammars, you know a lot of things about French, those rules that the French people don't even know. And then after so many years of studying whatever foreign language, French or whatever, and then you go to France and you don't know what they're telling you. For physics, we're going to do this kind of a general, it's not precisely comparable to the situation, but it's somewhat comparable. We're going to do this in a pretty quick fashion to give people an overall view of the situation they have to deal with in high school. This is obviously separated into several parts. One part is obviously physics. I mean mathematics, because physics without math is nothing. It's basically some interpretation which is never really true. And if you want to study physics, actually in today's world, if you want to study anything, you want to study economics, or you want to play stock market, anything that you want to do, probably there is a pretty healthy dose of math in it. Even if you say, I just want to be an artist. For you to be an artist, you really need to get a hold of color, and this thing about RGB color. I don't know. RGB means red, green, and blue color. I mean, red plus green equals to yellow. I mean, this sort of things. If you don't have a sort of a mathematical way of looking at it, and you're gonna end up having problems with it. And I know some artists, all they do is a set of colors, like 7 or 8 color tones, and they play among these tones, so they don't have to deal with a bigger picture. But that limits what they do, though. For instance, for some of the artists, when they move, they're gonna change their basic set of colors, and that is a problem. In other words, in terms of mathematics as logical thinking, everybody needs it today, and physics, you need it too. But we're gonna get at that later. Mathematics is used as a language for physics, and physics is probably the component for everything, because for instance, chemistry, right? Now today's chemistry is anything that deal with molecular interactions. Hydrogen plus oxygen becomes water. That sort of things are considered chemistry before it's become history. Before it becomes chemistry, it's really part of physics. At least the interpretive part of it. Maybe there are other things like biology or whatever. They may not really, because they study the macroscopic type of issues in a sort of applicational, practical kind of way. It may not have anything directly to do with physics, but physics is there. When you really get into, if you think chemistry is part of it, then physics is in it. And the other example is nowadays that then we're coming out of this biology realm. Let's just say, if you're gonna become a physician, maybe you can not study too much physics if you're not gonna get into cancer treatment. Because a lot of people, a lot of hospitals, they hire physicists to handle the cancer treatment stuff. If we don't talk about that area, if we go to, for instance, electronics, nowadays we're dealing with nanotechnology. That's a nanometer. That's 10 angstroms. The nanotechnology, it's basically maybe we can deal with that let's see. We can deal with that a little bit in when we go through the physics areas, because that's kind of a microscopic situation. Generally speaking, after we have mathematics, we deal with four types of physics. In other words, physics is separated into four general types. One is mechanics, that is how things move. There's a cart you push and it's going to move, and you want to study how fast it moves. You speak something, then you disturb the air surrounding you, and there is a sort of wave going down. That's sound. That sort of things. It's mechanics. And the second area is electromagnetism. That's when the let's say electron moves, when there's electrical current, there's magnetism produced surrounding it. That phenomenon, electricity caused, let's just say, when it's caused by electricity, that basically is everywhere. Everybody use cell phones. Everybody use all kind of electricity device. Even, for instance, even when we go camping, we probably will bring a charger these days, because we really cannot live without without these devices. Then there is a thermodynamics. Thermodynamics is sort of a statistical view on some microscopic movements. For instance, the air surrounding us, the air molecules move in a certain with certain velocities. Velocity is essentially speed with the direction. They move in all directions with all speed. Statistically, we feel such move. We call it temperature. However, a particular molecule can move fast, move slow, move in whatever speed. To study this, it's thermodynamics. However, we're not going to really get into this, because I don't think even in any case, the high school physics is not going to do it. I think even the college physics major will not do too much in this area. And then it's quantum mechanics. But before quantum mechanics, I want to say one thing. It's really belongs to the area of mechanics, but it's sort of modern in a way. So we'll talk about it here. That is, if we see a car moving, say, 5 miles an hour, if we run 5 miles an hour, then the car relative to us is not going to be moving. We're running with the car. That's our experience. However, if we see a light that's traveling at the speed of light, and then let's say we cannot move at the speed of light, because that takes infinite amount of energy to get us to do that. Let's say we move at a certain, somewhat close to the speed of light. We look at that light. The light still, relative to us, travel at the speed of light. In other words, there is a person looking at the light that travels at the speed of light. Another person that travels in the almost speed of light, looking at the same light. The light also travels at the speed of light. The light doesn't change. Of course, this only happens when you travel really, really fast. This assumption, this hypothesis, created the what we know as, what we call today as relativity. It's discovered by Albert Einstein. Okay. Then there's an area called quantum mechanics. Quantum mechanics is also against our intuition, but it's just in another way. in our lives, in any given time, if you know exactly when you tell me, I'm gonna know where I was, my position, my energy, my how fast I move, my momentum. You just tell me when. When the object is sufficiently small, then we have a problem. In other words, if you give me a time, I don't know. I don't know its energy, its momentum, its position, all of these things. You cannot know them at the same time. Of course, I'm being this is I'm just giving a general idea. The correlation is, for instance, time and energy, and position and momentum. They're not you cannot know it at a certain time, and the certainty of it. There's a relationship between those two variables, but we're not gonna get that. We just at least to get to the point that you give a time, you don't know where the thing is. You're not sure. This is experiment. You can do experiment and prove it. You let electron go through a narrow slit. That'll happen. You don't know where the electron is going to go, even if you know exactly how the initial position is. That's quantum mechanics. The study the sort of small objects. Those of us who have learned, who have heard of the nanotechnology. Nano means nanometer. That's 10 to the minus 9th meter. Normally we use angstrom. That's 10 to the minus 10th. The angstrom is we use that because the hydrogen molecule is about 3 angstroms in diameter. So that's basically the diameter of a hydrogen molecule, probably any molecule in that in that area. Hydrogen being a small molecule. DNAs and those things, or any kind of organic molecules, are big. 10 nanometers, which is 100 angstrom, that is close to molecules. There are things that are happening at that level. For instance, energy of the particle is no longer continuous. We know that you can be of any, if you move, right? You can move at any speed, any velocity, right? If you move at a certain velocity, you have a certain kinetic energy. You're moving energy. In other words, if I want to stop you, I have to put some energy out to stop you. In everyday life, we don't think that the energy can be no longer continuous. Actually, quantum mechanics, the word quantum comes in precisely this context, although it's a little different. Quantum mechanics, people learn that the electrons outside of a nucleus holds only certain energy levels. That's what quantum, the word, come from. But anyway, as we get into the smaller and smaller scale of silicon chips, so we can get faster and faster calculation speed and more memory. Quantum mechanics is really getting into our lives one way or another. But at least in high school, we don't have to deal with it. So we're not going to get into these areas. That is the overview of physics in general. In other words, we learn mechanics, which is how an object moves. That we will get into. We'll study that a little bit. Then it is electromagnetism. That needs a little bit sort of higher level of math that we're not gonna do, and physics. I mean, high school is not gonna do, college is not gonna do. So we're not gonna deal with that. Thermodynamics that needs serious statistics, we're not gonna do that either. And quantum mechanics, we're not gonna do that. Quantum mechanics deal with probabilities. You don't know where a thing is. When the electron is trapped in a molecule, you really don't know where it is. Not that we cannot detect. If our device is as precise as possible, you still can't figure out. You just cannot theoretically. You don't know where it is, and that is general area of physics. Other things are nowadays are split to other areas. For instance, we have biophysics. That's a subdiscipline. That's those parts that already got into biology. Then we have chemistry. Today, even the disciplines are get separated finer and finer. But what we're doing here is to get everybody a overall picture. That's what we want to do. In any case, this is the first. This is the introduction. It basically just blah blah blah. Starting next time, we're gonna have some. We're gonna have some real math out. If anybody has questions, at least in the during the time that we're doing this in 2018, please leave us a note, and we'll try to answer these questions. Otherwise, we're gonna start. We're gonna start doing this, and hope those people who get into this get some advantage, get some benefit out of it. And last but not least, I just want to say that we 3 years ago we did a Hamlet, Shakespeare's Hamlet, the play. It's also on YouTube. It's some hundred and some hours since it's very long. We went through every line. Anybody want to sort of take advantage of that? Please do. And anything that I've left out, drop us a line, and we'll try to communicate at least during this summer, 2018 summer when we're doing this. Okay, that'll be our introduction. I'll see you next time.